Hey everyone, in this video we are going to see how to use op-amp as a subtractor. So that is also called as difference amplifier. So it will take basically the difference between inverting and non-inverting terminals of the input and amplify that input depending upon the gain of the amplifier. So if we made gain equal to 1 at that time, the output will be the mere difference between input terminals, because the scaling factor or gain, which we call, it will be equal to 1. So it is multiplied with 1 and the output will be equal to the difference of the input signal. So by adjusting the resistances, that are these resistances R2, R1, R3, R4, we can make gain equal to 1. So how we are going to implement this as a subtractor, we will see in this video. So if you are new to the channel, please guys subscribe the channel, and if you like the content, press the like button. Okay, so this op-amp design amplifies the difference voltage between its inverting and non-inverting terminals. So, as I said, this op-amp design will amplify the difference voltage between inverting terminal and non-inverting terminal. So, it will take a difference of V1 and V2. So, at what will be the difference? That difference will be amplified by the op-amp here. Okay. So, circuit diagram is um, the first voltage is applied here, that is V1, and the second voltage is here V2, and the input resistance for first one is R1 and for second one R3. So here it is a voltage divider circuit, so the resistance here will be R3 into R4 divided by V2 into V2 here. So that will be the resistance across this terminal, that is here. So, and R2 is the feedback resistance which is present over here. Okay, so how to find the output voltage? So apply KCL at node A. So this is the node A terminal and we will apply KCL. So KCL says that the current entering the junction will be equal to the current leaving the junction. So current entering here is, I have taken as I1, and the current which is leaving this junction is I2. So I1 is equal to I2 is the equation, and when we write it in terms of voltage, it will be equal to V1 minus V by R1, which is equal to V1 minus V by R1 and V minus V naught by R2. So that is the voltage distribution law. Then separate these terms out, v1 by r1 plus v naught by, so I have to make v1 and v naught terms one together. So v1 by r1, v naught is taken this side, so v by r2 plus v by r1. So I want to make vv one side, so I will separate this. Now take the V naught terms to one side, that is V naught by R2 is equal to V by R1 plus V by R2 minus V by R1. So take the V naught common here, then R2 by R1 plus 1. So I have taken V common. So when we take V common and VLCM, then R2 by R1 plus 1 into V minus R2 by R1 into V1. So I will be left with this one. So further simplifying, V naught will be equal to 1 plus R2 by R1 into V minus R2 by R1 into V. So let us say this is the equation 1. Then apply KCL at node B. So we have other node called as B. So here I will apply KCL now. So the current entering will be equal to the current leaving to this ground portion, because no current will flow into the op amp here. So what I can write is V2 into V2 minus V dash divided by R3 will be equal to V dash minus 0 by R4, because this is something like this, right? So this is the op amp portion here, then this is R4 and this is R3, this is V2 and this is V dash, and this is connected to ground. So V2 into V2 minus V dash divided by R3, and this portion is, here it will be 0 volt, so ground means 0 volt. So V dash minus 0 divided by R4, this portion and this portion. So like this we can write the, this current is equal to this current, because no current will flow into the op amp. That golden rule we know. Okay, so let us try to simplify this one. So v2 by r3, take v dash one side, then take it as common, then v dash will be equal to v2 into r4 by r3 plus r4. So this equation will be getting. Now using golden rule of operational amplifier, that is voltage at two terminals inverting and non-inverting is equal. So the golden rule says that the voltage at its two terminals, that is inverting and non-inverting, is equal. So V and V dash will be equal to each other here. Okay, so V is equal to V dash. Then substitute this in the equation 1. So V naught will be 1 plus R2 by R1 R4. So this V dash we are gonna put there. So R4 by R3 plus R4 into V2 minus R2 by R1 into V1. Then V naught will be equal to 1 plus R2 by R1 divided by 1 plus R3 by R4 into V2 minus R2 by R1 into V1. Okay, now finally the output voltage is V naught equal to R2 by R1 into 1 plus R1 by R2 divided by 1 plus R3 by R4 into V2 minus R2 by R1 into V1. So this is the equation what we will be getting finally. Then as this is a difference amplifier, it should give zero output when both the input signals are equal. So as this is a difference amplifier, when inverting and non-inverting inputs are same, let us say V, then output V naught should be 0, because it will take the difference between the input terminals and then it will amplify. So if the difference is 0, then the amplification of 0 will be 0 itself. So this is what I'm saying. So if inputs are equal or same magnitude if they are having, then the output should be 0. So we'll take that case here. So if V1 is equal to V2, that is these two inputs V1 and V2 are equal to each other, then what will happen? So if to happen this, we have to take the resistances. R1 by R2 will be equal to R3 by R4. So here it will be R1 and R2 as I've shown earlier, and R3 and R4. So these resistance should be equal and these resistance should be equal, and their division should be equal to each other, that is R1 by R2 will be equal to R3 by R4. So equation C will become now V naught equal to R2 by R1 into V2 minus R2 by R1 into V1. Okay, so R2 by R1, R2 by R1, because V1 is equal to V2. Now we have taken, okay, so as the R1 by R2 is equal to 1, because they are equal, so 1 plus 1 will be 2 here, and R3 by R4 is also 1, so 2 by 2 will cancel each other, so R2 by R1 into V2 minus R2 by R1 into V1 will be left. Okay, so I can write V naught equal to R2 by R1, take it as common, because we have applied already R2 by R1 is equal to R3 by R4, so I can interchange them. So R2 by R1 is into V2 minus V1 equal to, so this is the output equation which we are getting finally. So V naught equal to R2 by R1 into V2 minus V1. So here this is the gain factor or scaling factor, and this is the voltage difference. Here R2 by R1 is scaling factor, so I have said that earlier also. So output as mere subtraction. So but I don't want this. So if I am implementing subtractor, then it will not make sense for me, because this is amplified and scaled by some factor, so I don't want any scaling in my output. So what I can do is I will make the gain of the op amp equal to 1 or unity. At that time the output will be equal to the mere subtraction of the input signal. So how I can make the gain equal to unity? So I just want to make this term equal to 1. So what I have to do? Simple, make R2 is equal to R1, then at that time they will cancel out each other and output will be the mere subtraction of the input voltages. So R2 is equal to R1, when we take, output will be equal to V2 minus V1. So this is how I can implement a subtractor circuit using operational amplifier. Now what will be the final circuit? So final circuit will be like this. These two resistances are equal to each other and these two resistors are equal to each other, and in fact these two resistors are equal when we want unity gain. So when I take this one as R1 and this one as R2, at that time R1 will be equal to R2, then only I am getting the unity gain, and the output voltage will be the mere subtraction of the input voltages. So like this we can implement a subtractor using the operational amplifier. I hope you like this video. Please guys hit the like button and don't forget to subscribe the channel. Thank you. Thanks for watching.